prove that the SD of the standard normal is 1. So all of those things need to be done, and at this point we just know the variable part of the standard normal density, e to the minus 1/2 z squared, but we don't know the constant in front of it that's going to make it integrate to 1. So let x and y be IID standard normals with density phi of x is c e to the minus 1/2 x squared, where c is a positive constant. The joint normal density then is c squared e to the minus 1/2 x squared plus y squared, for c some positive constant. So we're going to show that c is 1 over the square root of 2 pi, and that the expectation of x is 0 and the SD of x is 1. Today, student explanations to the concept test from last time will introduce the Rayleigh distribution, which will indirectly answer our questions about what C is, and we'll show that the sums of independent normal random variables is normal using moment-generating functions. So student explanations. So we had a concept question, S and T are IID exponential lambda, x is the min of st, y is the max of st, the joint density is as shown, the marginal density of x is. So one way to do this, as a student does here correctly, is you integrate out y, and the tricky part is the limits of integration. Since y is a max and x is a min, y is greater than x, so we're integrating y from x to infinity. Another student gets the limits of integration wrong and just integrates from 0 to infinity. That would be wrong. One student, without too much explanation, says from the Brian and Ye-Ming problem, but that's a good idea because x is the min of Brian and Ye-Ming, and we showed that x is exponential lambda b plus lambda y. So then the density of x would be lambda b plus lambda y e to the minus lambda b plus lambda y x. For us, lambda b and lambda y are the same, so we get 2 lambda e to the minus 2 lambda x. Onto the Rayleigh distribution. So let t be exponential 1/2. This has the density 1/2 e to the minus 1/2 t. The Rayleigh distribution is defined as the square root of t. So as an exercise in the change of variable rule, I asked you guys to find the density, and you did that beautifully. You can see that the density is r e to the minus 1/2 r squared for r greater than 0. It has this density, so this picture. And another way to derive it, you could square both sides of this probability that r is greater than r. Note that r squared is t, which is exponential 1/2, and we know the survival function for t is e to the minus 1/2 r squared. So we get then the CDF 1 minus e to the minus 1/2 r squared, and the derivative of that is the density r e to the minus 1/2 r squared. So the Rayleigh distribution will help us find the density of the standard normal. To make that connection, let's consider 2 IID standard normals, and let r be the square root of x squared plus y squared. So if x and y are the coordinates of the Cartesian plane, then r would be the distance from the origin to that point, to the point xy. So we're going to show that r is in fact Rayleigh. So the probability that r is dr, it's the volume of the cylinder under the joint over the shaded blue annulus. Now the joint here I'm writing with a c squared. We still don't know what c is. So that volume, the probability that r is in dr, it's the height of fxy above the blue annulus times the area of the blue annulus, which is c squared e to the minus 1/2 r squared times 2 pi r dr. You can see that 2 pi r dr is the area of the blue annulus. Do some rearrangement here, and you see that you get c squared 2 pi r e to the minus 1/2 r squared dr. And we recognize the Rayleigh density in there. If we integrate from r is 0 to infinity, our probability, that obviously is 1. And taking out the constant, you can see that the integral of the Rayleigh is 1. And so all of a sudden we have that c is square root of 2 pi. Beautiful. So our conclusions, we've done actually three things. Well, we've done two things here. X and Y, IID standard normal, t exponential 1/2. We've shown that square root of x squared plus y squared and square root of t are both Rayleigh distributions. So in particular, x squared plus y squared is a gamma. Interesting. Furthermore, we have now established the density of the standard normal. Phi of x is 1 over the square root of 2 pi e to the minus 1/2 x squared. And the expectation of x is 0, the SD of x is 1. I want you to take a look at the end of these notes. I've very clearly written out the proof of that. So here's an application of the Rayleigh. So we throw 12 darts at a target. Suppose the distance that each dart is away from the bullseye follows a Rayleigh distribution, and the distances are independent of each other. Let x be the third closest distance and y be the seventh closest distance among the 12 darts to the bullseye. Find the joint density of x and y. So x here is the third order statistic, and y is the seventh order statistic of the Rayleigh. So I've been teaching you how to do this. You are throwing 12 darts at the Rayleigh distribution here, and we're told that there's 1 in dx, 1 in dy, so that means there's 2 before x. There's 12 darts total, so there must be 3 between x and y and 5 after y, because we know the seventh dart is in dy. And so the chance that a dart lands between 0 and x is just given by the CDF of the Rayleigh. So because 2 darts land there, the chance that 2 particular darts land there, we square. But actually, there are many different combinations of darts landing in the different regions. So there's 12 choose 2, 1, 3, 1, 5 for the different 2, 1, 3, 1, 5 that we have above. And the probability that a particular dart lands in dx would be the density of the Rayleigh times dx, and the chance that a dart lands between x and y is the difference of the CDFs at x and y. So I'm going to cube that, and similarly for the rest of it. So just lastly, the chance that you get 5 darts greater than y would be 1 minus the CDF of y to the 5th power. So now I just substitute in the density and the CDF and the survival function into here, and we're good to go. So as another application, suppose 3 shots are fired at a target. Assume for each shot both x and y are standard normals. Let w be the closest distance among 3 shots to the bullseye. Find the density of w. So w is the min of these 3 Rayleighs. And so I can think of 2 straightforward methods to do this. One is just to use the CDF, because we have a min, and it's often you want to use the CDF to find the min. So the probability that W is greater than W is the probability that R1 is greater than W, R2 is greater than W, R3 is greater than W, which is the probability that R1 is greater than W cubed. R1 is Rayleigh, and we know the survival function for that. So we just substitute that in, and then we can find the CDF and hence the density by taking the derivative. Another method would be just to use Rayleigh ordered statistics. And so the probability that W is in dW is proportional to the probability that we have R in dW, R in W, and R in W. And so the constant is 3, choose 1, 2 here that I'm not writing. And so the probability that W is in dW is that constant times WE to the minus 1/2 W squared dW, which is the probability that R is in dW, times the probability times the survival function squared. And work that out and you get exactly the same density. So finally, we started working on sum of independent normals and showing that that is normal. I did a quick review of the MGF, namely the MGF of the standard normal is e to the t squared over 2, and the main properties of MGF that if x and y are independent, then the moment generating functions multiply. So the moment generating function of x plus y is the product of the moment generating functions. The equality of two moment generating functions if and only if those two random variables are equal in distribution, and the moment generating function of b plus ax is e to the bt, the moment generating function of x of at. So I defined what a normal random variable is. We just basically make a change of scale of the standard normal. We know the density of the standard normal, so by the change of variable rule, you get the density for the normal, and you can find the MGF of the normal, and so you guys did that brilliantly, just using that third property highlighted above. And so we get e to the mu t, e to the sigma squared t squared over 2. Then I asked you guys to use the MGF to prove that the sum of two independent standard normals is 0, 2. And so here Z1 and Z2 are independent standard normals. We know they're moment generating functions. We just take the product of them, and we can write this in the form of the moment generating function for a normal. So that proves that it's normal 0, 2. Finally, we showed that if you have two normals, then any linear combination of those two independent normals, any linear combination of those two independent normals is normal with mean the linear combination of the means and variance a squared sigma 1 squared plus b squared sigma 2 squared. So this is a very easy proof. We have the moment generating function for x1. We can figure out what the moment generating function then for ax1 is. And then ax1 and bx2 are independent, since x1 and x2 are independent. So the moment generating functions just multiply. I know those moment generating functions. I plug them in. I rearrange things. And I can see that this is exactly the moment generating function of a particular normal. In particular, I can just read off what the parameters are. I can see that the mean is mu1a plus mu2b, and the variance is sigma 1 squared a squared plus sigma 2 squared b squared. that's the show today. We've done a lot. Have a great day.